So I'm Chris Kachris and co-founder of Inaxel, and this presentation is about on how to speed up your Spark applications using FPGAs in the cloud. So the title of the presentation could also be how to speed up your Spark applications without changing, without increasing your cost, your operation expenses, and without changing your code. This is the most important thing. You don't have to rewrite your code or to modify your code in order to speed up your application using FPGAs. So first of all, why to accelerate? Why to speed up your applications? So according to a survey from Databricks, 91% of the Apache Spark users, they care about performance. Okay, so they care about how to run much faster their application. They care about to get the results much faster. And they also care, 69%, they care about ease of deployment, and 76% of the users, they care about ease of programming. So they don't just care about how to speed up their application, but how to speed up their application easily without changing their code and rewriting the code. So in order the data centers operator to allow users to run faster their applications, they have started adopting and deploying different kind of hardware accelerators in the data centers. So currently they started, first they started with GPUs, general purpose GPUs. Now some of the data centers operator, they are also deploying FPGAs in order to allow users to speed up their applications. So there's a new emerging domain that has started on specialized heterogeneous data center systems. This is in order to allow users to run much faster their applications. So currently, Amazon was one of the first ones that deployed FPGAs into the data centers using some Xilinx FPGAs, I think. And soon other companies like Alibaba, Huawei, Baidu, and other companies have started deploying FPGAs into the data centers, and they are allowing users to use FPGAs in order to run faster their applications. Now, if you are a Spark user, the available frameworks in order to use to run your application are the CPUs, GPUs, and maybe FPGAs. So CPUs provide much faster, much higher flexibility because it is based on programming on the widely used programming frameworks, but they don't have so much performance as GPUs and FPGAs. GPUs are also flexible. Okay, it is they are programmed using CUDA or OpenCL, and they provide a good performance, but they are still expensive. They consume a lot of power, and they are hard to program compared to Python, Java, etc. And then you have specialized chips like TensorFlow, or you have FPGAs that provide much higher performance, but they are much harder to program using hardware description language like VHDL and Verilog. So what is the best approach? The best approach is to have a hybrid solution. That means that you combine the best of two worlds. So you combine the flexibility of the processors with the high performance of the FPGAs. And this is what Intel and other companies promote. They promote the use of both processors and FPGAs. The processors are used to run the most typical software stack. And then you are using FPGAs to offload the processor and run the most computational intensive parts. So what we're working in Inaxel is exactly on is for this platform. So we are developing, so we help companies speed up their Spark application or their machine learning applications by providing ready-to-use accelerators as a service in the cloud. That means you don't have to know anything about FPGAs. You don't have to know anything about how to transfer the RTDs from the host to the FPGAs or to the GPUs or whatever. So you only care about how to speed up your applications. And what we do is that we provide a ready-to-use IP cores in order to speed up your applications. So we are mainly focused on machine learning kernels. So machine learning library is widely used from the Spark community, and this is one of the reasons that we choose to focus on machine learning library and specifically on MLlib. And we provide IP cores. We started with Amazon AWS, and soon we are going to support many more data centers. So the idea is the following. You don't have to change anything at your code. So the idea is that most of the code will still run on the processors. And whenever you have a kind of a computational intensive task like regression, clusterings, recommendation engines, that it is very heavy, this one can be offloaded to the FPGAs in order to run faster your application and offload the processor. So what it is the framework that we're using? So it is based on the Amazon AWS systems. So far as you know, whenever you have to deploy a software framework into Amazon AWS, you just have to download the Amazon machine image, and this will be downloaded to a specific platform, a specific processor, and then you are ready to run your applications. So we follow the same approach. Amazon follows the same approach, but instead of the machine image, they provide this Amazon FPGA image. So basically, it's the configuration file for the FPGA that has been wrapped for the Amazon FPGAs. So the idea is that you can, in the same way that you can download the Amazon machine image, in the same way you can also download the Amazon FPGA image for the FPGA platforms deployed into the marketplace, into EC2 FPGA. And you can download it from using AWS Marketplace, and then it's very easy to use. So what is the process? The process is that you can run your Spark application as usual. So you can rent one of the machines in Amazon, like a C4, M4, or whatever. You can start running your applications. And on top of that, the only thing that you have to do is also rent the FPGA instances in AWS, like the F1. And you just need to download in Axel's IP core from the Amazon Marketplace. Okay, and that's it. Whenever you have some specific application that it is very heavy, like logistic regression, k-means clustering, etc., instead of running this specific kernel on Amazon AWS on the processors, it will be offloaded to the FPGA platform. And then it will transparently run much faster. Okay? So far, we have developed 3 IP cores that it is widely used from the Spark community. The first one is the logistic regression that allows, it's basically on gradient descent regression for faster training of machine learning algorithms. So this can be easily modified to support different kinds of regression, like linear regression, etc. We also support clustering algorithms. So far, we have implemented k-means clustering, but again, it can be modified to support any different kind of clustering algorithms. And we are also working on recommendation engines based on collaborative filtering. And we are mainly focused on an alternative list square recommendation systems. Okay, and this is something that we are working now and will be finalized in the next couple of weeks. And we will also upload it into the Amazon Marketplace. So, as I said, we are mainly focused now on MLlib. So we try to be compatible with Apache Spark frameworks and the libraries, so you don't have to change anything in your code. So currently we support MLlib, the machine learning library. We're working also on some frameworks for SQL, GraphX, etc., but still this is in early mode. So currently we have, as I said, logistic regression, recommendation engines, k-means clustering, and soon we are going to also to deploy several other modules that are compatible with the Spark MLlib framework. So what we have managed to do is that compared with the processor frameworks like the C4 in AWS having 36 cores, or M4 that it has 16 cores in AWS. So we have managed to achieve around 2.7, around 3x to 10x speed up for different kinds of applications. For logistic regression, we target around 3x speed up, and depending also on the data set, on how large is the data set, the type of the data set, etc. We are also working on some different kind of algorithms that we can achieve much better speed up. So what it is the drawback? Of course, we are talking about hardware. Okay, so that means it isn't so flexible as it is the software, and that means it has some restrictions. So, for example, for the logistic regression, currently the architecture that we have can support around up to 784 features and up to 30 classes, and almost the same applies for the k-means clustering. It can support up to 30 clusters. That means that the same FPGA image, the same AFI, can be used for this kind of application, having up to 800 features and 30 classes. If you have a different kind of application that needs more classes or more clusters, the only thing that you need to do is to let us know what is the maximum size that you want to support, and we will just recompile our framework in order to meet your application requirements. So how can we achieve this speed up? So basically what we are doing is we try to explore the parallelism of the FPGAs. Okay, so we take the algorithms, we try to parallelize it as much as it is possible. So we make different kind of application-specific circuits for the FPGAs that are well aligned with the application requirements, and then we program the FPGA. So for the logistic regression, we transfer the algorithm into circuits to digital logic, and then we have managed to increase the performance of the system, although that FPGAs runs at a much lower clock frequency than the processors. Okay. So the architecture is straightforward. So you have the FPGA communicating with the processor, the host processor, through PCI Express. And the idea is that whenever you want to offload the processor and speed up some of these kernels, you transfer the RDDs through PCI Express to the FPGAs. The RDDs will reside into the DRAMs, and then you do the processing. So the FPGA will get as an input the weights or the centroids, if it is the clusterings, the data, and then it will export the gradients or the counts, right, for the clustering. And this is pretty straightforward. So, as I said, we have already uploaded our IP course into Amazon AWS Marketplace. So feel free to download it and test it. It is for free for the first 20 days, I think. So you are welcome to download it and test it and give us some feedback on this one. And let us know what are your application requirements in order if you want to modify some of the kernels in order to support your code. So you can download it and you can test it. So the most important thing is that it is fully compatible with the Apache Spark framework. That means you don't have to change your code, and this is very important. So the machine learning library, the accelerated machine learning library that we have developed is fully compatible with the Spark framework. So we have developed all the APIs that it is required in order to allow the seamless communication and integration with FPGAs. So as an example, I can give you an example for Scala and for Python. So the only thing that you need to do is just add one line of code. You just need to import our library, the Inaxel library, in order to allow the offloading of the kernels, of the machine learning kernels to the FPGA. Basically, what we are doing is kind of overloading this kernel. So whenever the processor sees, for example, the training for the logistic regression, instead of running it into the typical processor system, it will be offloaded to the FPGA. So we basically do offloading of the machine learning library kernels, right? So this is the example for Scala. It is almost a similar example for Python. So the only thing that you need to do in your Python code is just to add one line of code that includes our APIs, our machine learning library, that allows you to offload the processor using the FPGAs. So you can do it either using Spark or standalone, so whatever you feel more comfortable with. So we have developed and we provide all the APIs for Scala, Python, Java, C, C++, and of course Spark. So we have two flavors that you can download from Marketplace. One flavor is that as a standalone using the APIs for Scala, Python, Java, and C++. And the other flavor is integrated with Spark. So you can download the AMI and the AFI that has precompiled and preconfigured the Spark that can be directly communicate with FPGAs. So just let me give you just a very small demonstration of this one. So on the left side, you can see this is the demonstration for the logistic regression running on a C4 machine that it is cost $1.6 per hour. And on the right side, you can see exactly the same application that it is running on a F1. The F1 has 8 cores, so basically there is an Intel processor with 8 cores, plus the communication that it has with FPGA, plus the FPGA. So as you can see, let me just put it again. So as you can see, the left one, the C4 start faster because it has 36 cores, so it can run much faster the extraction. But as soon as the F1 starts, it can run much faster the 100 iterations compared to the C4. And why is that? Because the iterations are being offloaded to the FPGA, and then it can run much faster. So in this case, you can see that when it comes to around 36% of the time for the C4, the F1 system has already finished. So it is when it goes to 32%. So this is how we achieve the 2.8x speed up compared to the F1. So as I said, the most important thing is that allow the seamless integration with the Spark and with Apache Spark. So the only thing that you have to do is, if you download our libraries, is that you can execute a single script, and it will set up the Hadoop and the Spark framework, and it will format the Hadoop name node, and will upload all the necessary data sets to the HDFS. It will also configure the FPGA, because this is something that it takes some time in the first time that you have to configure the FPGA. And as soon as you have it, as soon as you have configured the FPGAs, then you can speed up your application, and you can run much faster your applications. Okay. So we have full documentation on how to use this library. So as I said, we have the documentation and the APIs for different kind of programming language, whether you want to use C, C++, Java, Python, or Scala. Okay, so we have developed these APIs. So you can seamlessly integrate the FPGAs without having any prior knowledge on how to program FPGAs, on how to send the data, the RTDs from the host to the FPGA, etc. So as I said, we are currently supporting classifications, regression, recommendation engines, clustering, and soon we are going to have also some decision trees kernels. So far we focused mostly on the most widely used kernels. So the one that is most widely used are logistic regression, k-means clusterings, recommendation engines based on ALS, etc. And soon we are going to have also the decision trees and other frameworks. So we also plan to integrate it also to different kind of frameworks like Cafetooth, Not, Torch, Mahout, Keras, etc. So it's still the only thing basically that you need to do is just change the APIs, right, in order to support these different kind of frameworks. So the kernel remains the same. And then you can run it and you can speed up your applications. So if you are interested in speeding up your applications, so please contact us, and we can give you a free demonstration on how to speed up your applications without changing the cost and without increasing your cost. So you can see it as a two-way. Either you can speed up your applications running on F1, or at the same time you can reduce the cost by using, for example, F1 instead of using 4 times or 4 modules of C4 or 3 modules of C4. So if you have any questions, or if you have any other questions, so please let us know or send me an email. Thank you very much.
So are you able to scale beyond one node?
Yes, so it is basically fully scalable. Okay, so we have all the required modules that in order to support fully scalably. So it is basically integrated with Spark, right? So if Spark is deployed into 4, 10, hundreds different machines, if it is on F1, then it can be deployed and can be scaled to different nodes.
Yeah, because K-mean for iteration need a data exchange across the different partitions. So you actually have some components running on the journals.
Exactly, you are right on this one, but as long as the K-means clustering has been sent to different kind of nodes, all of these nodes can run in parallel and can do a portion of this clustering, right? And then, of course, all of this will have to be reduced into a central node, okay? But the reduced states can also be offloaded to the FPGAs.
For the RDDs that you were sending to the FPGA, did you have to dereference the RDDs, or you're actually doing that in the FPGA?
So you have to transfer So you have to transfer the RDDs into the DRAM in order to have faster access and faster communication between the FPGAs and the DRAM. Okay, so if this is what you are asking, so you have to transfer the RDDs into.
Let's let this gentleman finish his question, and then we'll...
Right. I don't know if the question was clear. So you have the RDD, obviously it's a pointer. So are you dereferencing that pointer on the FPGA?
Yes.
How are you doing that actually?
Yeah.
But I'll sync up with you offline. But my other question is, you had a list of different machine learning algorithms that you guys have built. Was there any reason why you did not consider CNNs or DNNs maybe?
Okay, so CNN are a different algorithms, so we plan also to have some IPs for CNN also. We started from this one because it is the most widely used for this one, but also CNN are widely used, so we plan also to have it in the future, CNN.
Hi, in your architecture diagram, you said that you instantiate a C4, M4, or S4 instance and then offload the computation to F1. Yes. And in your comparison, you showed F1 versus C4. So in that comparison, does it mean that the F1 still uses the C4 instance?
Yes, you are right on this one. So the real comparison is between C4 and an F1. So basically, okay, you are right on this one.
C4, C4 plus F1.
Yeah, okay. C4 against F1. Okay. So you don't have to use C4 and F1. You only have to use F1 instead of C4.
Okay, but your architecture diagram...
Yes, you are right. I will make it
and
more clear.
The memory was the same across them? Because I know that the F1 instance has lower cores and more memory than C4 instance. What was the memory on C4 when you did the comparison? What was the memory?
What was
memory, RAM.
It's... I think it's 8 gigabytes per bank, but I will check.
Okay, because F1 has 200 gigabytes. Yeah, thanks.
Because you mentioned your FPGA use PCIe directly get the data from the host memory, if I can say that. So the RDD actually is a very high-level construct. So even as the virtual memory, the Java, on FPGA, you don't have the TLB, for example, page. So you actually use a custom RDD, right? Require the data to put into your RDD first, right?
Yes, so basically this is a problem that you have to transfer RDDs to FPGA. If we have in the future a novel framework, another framework, or another platform that support, for example, cache coherency between the FPGAs and the processor, then of course this can help a lot to speed up even more the applications, because then you don't have to transfer the data between the processor and the FPGA.